walk through a couple examples of dealing with the moment of inertia for a wedge. And so this is an example of what they mean by a wedge, just a triangle. Now, the generic idea here is that the moment of inertia is equal to our lambda value x squared dx from our left bound to our right bound. Now, when we're talking about a wedge, there's two lambdas. Now, this lambda is basically an equation for the height of this wedge at any given x value. So if I have something like this, that is going to be a linear equation, something like ax squared, where a is the slope. Now, if I add an intercept in here, it just makes my math a little more difficult, so I'm guessing we're not going to have intercepts on that. Or if I have something more like a part of a parabola, it's going to be ax squared. So we're going to do an example of each of these for this setup. So let's start. So I have a wedge. I'm going to find the moment of inertia about the end. So just as before, we're going to choose this location as our 0 point and then identify our left and right bound. So if you wanted to do it about the center, this would be like 0 and this would be negative, say whatever the length is, L over 2, and this would be positive L over 2. So in our example here, where did my marker go? There it is. I'm going to go from 0 to L. And I'm going to say this is some linear function. So I have from 0 to L of ax times x squared dx. So because I have a straight line there, this is a linear function. And again, we're going to leave off any intercepts just to make our math go a little bit smoother for ourselves. And so if I integrate this, I'm going to have ax to the fourth divided by 4 plus any c, but because we're going to be doing a definite integral, we're just going to have our 0 to L here for our moment of inertia. And as you can see, that's going to make itself out pretty quick that I is going to be 1/4 a L to the fourth minus 0. So this is where we're going to start. Now there's two directions they can take us from here for a question. They can give us an a value, or they can have us deal with an m, and they want it in terms of m, not in terms of this slope. So let's pick an a value. I'm going to say they give me an a value of something like 16 over L squared. That's the example that I found that we're going to do. All right, so if I plug that in, I now have I is equal to 1/4 times 16 over L squared times L to the fourth. And I see that I end up with some of my L's canceling out. My 16 gets a little bit smaller, so I end up with an I value of 4L squared. Whatever their L value is, they are going to want to cancel out some of those L's so that you get that L squared relationship. So what this is telling me here, this 4, is this is telling me about the fraction and the mass. So what we want to do now is we want to see, how do you solve this with the mass? All right, so if I want to solve this with the mass, so let's kind of do that same idea. So mass is going to be our integral of our lambda dx, that linear mass density dx. All right, so in order to do this, I'm going to go from 0 to L. And so I end up with m is equal to ax, squared over 2. So remember, lambda was ax, so when I integrate that, and then we're still evaluating from 0 to L. I guess I should have substituted in there ax. Oh well. So now my mass ends up being a times L squared over 2. So now that I've found that mass, what I want to do is I want to solve for a so that I can substitute it back in here. Okay, so a is now 2m over L squared. So now it's kind of like what we did here. They gave us that value. So in this case, their m must have been 8. All right, so now I can plug that back in. So now I have my I, and I'm coming back from here. 1/4 times 2m over L squared, L to the fourth. Get rid of some of those L's, good. Get rid of some of those values, and I get an I of 1/2 mL squared there. Okay, so that is how I do it for a wedge that is linear. So what we're going to do next is we're actually going to set it up for a situation like this. So let's go ahead and erase this and set that up. All right, now that we have this set up, we're going to look at a scenario where it's curved. So we're looking at a parabola. So now my lambda value is ax squared. So let's go ahead and do the same kind of strategy we did last time. We're going to find our moment of inertia, and then we're going to look at two scenarios. One where we're given an a value, and one where we're going to find the mass and substitute that in. So we get something in that format of fraction, mass, length squared. All right, so let's go ahead. So in this case, we have a little bit different scenario. I'm still going to take it from the end, so I'm going from 0 to L. Remember, you always choose your axis of rotation as 0, so if you pick it somewhere else, you just have to make your bounds based off of that. So then I have ax squared times x squared dx. So I already have x to the 4th, so now it's going to go up to x to the 5th. That's why we have an L cubed over here, so that we can get back down to that square value. So now I have 1/5 ax to the 5th evaluated from 0 to L. Nice for us. Makes it a little easier if we don't have those bounds and we got to do a whole bunch of extra algebra here. So I have 1/5 AL to the 5th. Now if they give me an A, I just have to substitute that in. So my moment of inertia is going to be 1/5 times 10 over L cubed times L to the 5th. We see we get back to that L squared. That's important. And that drops down to a 2. So our moment of inertia here is 2L squared. Again, we need something times L squared. Now, if it's going to be a mass, it's going to be fraction times mass. So if I think about what that fraction times mass is, that's where that 2 is coming from. So same kind of pattern over here to find that mass. So my mass is going to be the integral of lambda dx. So my mass here is the integral from 0 to L of my lambda, which was ax squared dx. So my mass comes out to be a times L to the 3rd divided by 3. Okay, now I need to solve for a and substitute in. So it's this little extra step where we got to get to an a value, then we can plug it in. It's just our a value will have a mass in it. So my a here is going to be 3m divided by L cubed. Substitute that in, so now my moment of inertia is 1/5 times my a value, which is 3m divided by L cubed times L to the 5th. We're going to get rid of some of those L's, so we get L squared here. So we end up with a final moment of inertia of 3/5 mass L squared. Again, that follows our pattern that we want a fraction times the mass times the length squared. So those are the two examples for a wedge. Again, if we wanted to, we could add in an intercept. Again, that's just going to make our math longer, or we can choose a different moment of inertia about location, like an axis location. So maybe over here, changes our bounds, just adds more math, but the process is the same. Okay, there you go.